See, that's why it's good to have cookies beforehand, and then people show up and they're already here, you see.
Fair point.
Hey,
How you doing?
I'm good. Good to see you. I'll be around for a while. So.
I have no vested interest.
Oh, no, not at all. Yeah.
Although I do talk to Peter Bodenheimer every week.
Oh,
And
nice.
that guy's still going in his 80s.
Oh, yeah. Peter's excellent. So.
We're doing sad. We got tired of that too.
Okay.
I'll be about halfway, like 30 minutes.
You're gonna miss the best part. No.
Reconvene, guys.
You'll be to sit
We
there.
won't tell you what happened.
Okay.
We'll figure out the rest of the story.
Okay.
Yeah.
That's gonna look especially bad because the first half is the stuff I did with you, and it looks like you're gonna leave as soon as I start. We can start a minute late, so. Yeah, I figure you should.
Let us begin. I have the pleasure of introducing Fred Adams as our speaker today. Fred is a professor of physics at the University of Michigan. He's also the director of something called the Lineweber Center for theoretical physics at the University of Michigan. Fred had got a big part of his start at University of California at Berkeley during the heyday of star formation. The model Frank Shu and others were coming into prominence. And Fred's PhD thesis was to calculate the spectral energy distribution of these just formed stars, as well as the new stars plus their disks, as well as an additional component on gravitational stability. Those interests have broadened to include other aspects of star formation, especially clusters, understand cluster dynamics. He works on extrasolar planets and their formation. We're going to hear a bit about that today. And as many of you saw in my email to the department a couple of days ago, the list of topics that Fred is interested in extends for several lines and includes several topics in cosmology. So I'm going to leave the introduction there, and we look forward to a great talk from Fred. Thank you.
Okay, well, thank you, Andrew. Thank you so much for having me over to give this talk. It's always a pleasure to visit Caltech and the astronomy department in particular. So let's jump right into it. What I'm going to do today is basically twofold. I'm going to begin with an introduction. So I'm going to talk a little bit about the current observational picture for exoplanets, and I want to make the contrast between the top-down and the bottom-up scenarios for planet formation. And then I'll give you a brief overview of the core accretion paradigm for planet formation. As you'll see, there's lots of planets, and they probably form through several different mechanisms. Everything I'm actually going to tell you about new today is concerning the core accretion paradigm. And within that framework, I'm going to tell you about two results, which can briefly be described as this. The first is that, as Andrew was talking about back in the 80s, we were putting together a theory of star formation, and we're trying to understand the nuts and bolts of how that works. What I'd like to do for you today is to do what I'd like to do, not that I can do, but I'd like to do, is to do exactly the same thing for the planet formation problem that we've done for the star formation problem. And that will be the first half of this. The second half is once you've got a picture of, in this case, planet formation in place, the thing you really, really want to know is what sets the distribution of masses of your objects. So in the case of planets, what sets the distribution of masses of planets? And I'll begin to do that at the end of the talk. And I'll run out of time, which is probably appropriate because the second half, the theory of the planetary mass function, is not as secure as the rest of what we're going to talk about. Okay, so that's where we're going. Let me begin with a quick shout out to my collaborators. I'm going to steal material freely from papers written with these characters. Some of them you know, some of them you don't. Arthur was a postdoc at Michigan. He happens to have a similar name to me, but otherwise, that's it. Right? So, everyone says, "Is he your son?" He's not my son. I do have a son, but it's not him. So anyway, you have seen this plot. Probably one version of this bazillions of times. So we have this whole host of planets. And what we want to do is we want to make sense of how they actually got there. So let's begin at the beginning. Turns out the planet formation happens within something called circumstellar disks. And the initial conditions for the planet formation problem are set by the properties of these circumstellar disks. Back at my thesis, we were actually trying to make spectral energy distributions of these disks, and we made predictions for how big they are. And it turns out that 2 decades later, when you measure them, they're 100 AU, just like we said. We have much data on this process. We have looked at circumstellar disks left, right, and sideways. A lot of the work is done here. There are people in the audience who know far more about the observations of this than I do. But what I'm going to give you now is a theorist's quick and dirty summary of the observational picture, which I'm sure the expert observers will find some objection to. But nonetheless, this is going to be our starting point. So star formation takes place, or naturally produces these disks because of something called conservation of angular momentum. And these provide the initial conditions for planets. Now, the basic properties we have are that the disks extend from about, we'll have outer radius in tens to perhaps 100 AU. The typical size of a disk is 100 AU. The disks have a starting maximum mass of only about 1/10 of the stellar mass. What we see is that the disks have a starting mass perhaps as large as that, and it goes down from there. So when you look at the average disk and look at the average disk mass, it's going to be a much smaller number, but that's the upper envelope of the mass distribution. We think we can see the surface densities of these things, and they seem to have more or less power law surface densities. The index can vary between 1 and 2, depending on the disk and the observation and exactly what question you ask. And these disks live for millions of years. As I'll argue near the end of the talk, if you want to put a distribution on it, the lifetime distribution is almost an exponential distribution with a half-life of order 3 million years. Okay, so this is where we're starting with for our disk initial conditions, and we want to make planets within them. And somehow we have to get from a disk with the size 100 AU, which will then collapse its rocks into gravel with the size of 1 centimeter, and end up with something more or less the size of Jupiter. On a different observational front, you can ask, well, where are the giant planets? Remember, the first giant planet we found was 51 Peg, which was at a 4-day orbit, which seemed to like throw everything that we used to know about planet formation into disarray. Now, in recent years, starting in, well, this one's in 2019, we have enough data that we can look at the distribution of where planets are, and these are giant planets. And after all these years, they seem to be at 3 to 5 AU, not 4 days. And if you look at other studies, there's ways to do this, lots of curves on this. But the bottom line is that giant planets seem to form with a peak around 3 to 5 AU, which is conveniently just outside the ice line, which is exactly what we wanted. See, this thing has come full circle. In the 80s, we knew that giant planets formed at the ice line because that's the only logical place to form them. And then we found all these hot Jupiters that sort of threw everything in disarray. And then after all this, we look at the distributions, and guess what? It peaks at the ice line. So we want to make planets at the ice line. Now, how do you do it? Well, there's 2 ways to do it. We can do it from the top down, and we can do it from the bottom up. The bottom up is the core accretion paradigm, which I'm going to spend most of my time talking about. Let me talk a little bit about the gravitational instability so that I can dismiss it. What we wanted to do in the 80s was we wanted to make binary stars by gravitational instability, and it doesn't work. If you have a disk and a self-gravitating, what you naturally get is a brown dwarf. In order for the disk to be heavy enough to self-gravitate, it has to have a good fraction of the stellar mass, and it's going to set up an instability set by the orbit time of the outer disk edge, which is 100 AU, and that's going to give you a blob at 100 AU that the natural size scale is about 10 Jupiters. Now, this was really, really, really primitive numerical simulations that we did 30 years ago now. Dial forward a couple decades, and Zhao and Zhu did the calculation right. And what he found is that you form brown dwarfs at 100 AU. And then if you look at observations, what you see for the image planets are basically brown dwarfs at 100 AU. So what I'm going to argue is that the gravitational instability mechanism gives you, wait for it, brown dwarfs at 100 AU. Now that's great. It's something that happens. This does work. We see some of them. I learned today that some of the planets I just showed you might have high metallicity, so there might be a little bit more complication in that particular system. But nonetheless, most gravitationally formed planets are brown dwarfs at 100 AU. However, most planets we see are at the ice line. And they're not brown dwarfs, they're Jupiters. So if you want to form a Jupiter at the ice line and not a brown dwarf at 100 AU, you need another mechanism. And that's the core accretion paradigm. So back to our slot here, the brown dwarfs at 100 AU, which are the image planets, live up there. That's not what we're going to talk about today. We're also going to only talk about the formation of giant planets. So I'm going to cut out the inner or the bottom part of this plot. So everything that I talk about today only applies to the planets that are left in here. Some of you will argue that what I talk about today also doesn't apply to them, but I'm going to do what I can, okay? So having said that, let me give you a quick review of the core accretion paradigm. So the core accretion paradigm takes place in what can be organized into 3 stages, which are conveniently called stage 1, stage 2, and stage 3. So in stage 1, the idea is that the rocks or rocky bodies coagulate into a big core. The core is of order 10 Earth masses. At that And not a lot happens until you get to about 10 Earth masses because the gravity is not strong enough to hold on to gas. And it's just a rocky thing or a high metal thing. But once you get large enough, the growing core can hold on to some gas. And it enters into the second phase, which is called phase 2. In phase 2, you have a hydrostatic, or more or less hydrostatic, atmosphere around the core that extends all the way out to the Hill radius. And is very tenuous and hot and cools very slowly. So the tenuous outer atmosphere keeps accretion in check so that the planet cannot eat mass very quickly. It has to let that atmosphere cool for more stuff to come in. Now, as that atmosphere gets bigger in mass or heavier, it can condense more, cool faster, and more stuff comes in faster. Now, it might not be a clean transition between phase 2 and phase 3, but if you wait long enough, you get a slightly different configuration where that atmosphere has collapsed and material can come in rapidly. And that's phase 3. The reason why I'm being slightly careful about explaining this is that I'm only going to talk about phase 3. So everything that I'm going to talk about has assumed that this forming planet has already made a big core. It's already got enough mass that it's squished enough that material can enter into the Hill sphere rapidly. And that's the stage that we're going to talk about. That's also the stage that's relevant to what we're concerned with today, because that's when most of the mass of the planet is gathered. Okay? So just schematically, we have these 3 stages. If you look at what it looks like in time, we can plot the mass in rock and gas and both as a function of time. So first you have all rock, start to get gas, and then once you reach sort of equal amount of mass in rock and gas, you can start to accrete rapidly. What's significant is that it takes a while to reach this final stage. That time will become important once we talk about the mass function at the end of the talk. But before we do that, what I want to do is I want to revisit this latter stage of the planet formation problem and see how well I can actually calculate it from first principles, okay? Or from basic analytic considerations. Now you might ask, well, why am I doing that? Why don't you just put it on a computer? Because that's what everybody ever says to me every time I do a calculation, right? And it's a good question. It's great to put stuff on computers, but the current state of the art, I would describe this way, and some of you may disagree. People do calculations of the planetary structure itself down on the size of the planet, but they use spherical models and they feed material into it by fiat. In other words, they just put it as an outer boundary condition. That's great for calculating the structure of the planet, but it doesn't tell you how it got there because that's what they put in. That's fine. The other class of simulations that people do is they make a disk simulation and they have a seed particle that will become the planet, and they look at stuff coming in the Hill sphere and landing. And that's all well and good too. The problem there is that they can only do so much resolution and so many orbits. You only get a handful. Somebody said 100 orbits, but most are only like 10. And you have a high resolution simulation with several cells across the Hill sphere, but often it's only 6. So you can't really resolve the things that I'm going to try to calculate today with current state of the art. Very soon you will be able to, but in the meantime, we really want to know what depends on what. So it's useful to have a physical description, an analytic description of how this all takes place. And we really just want to see how far we can get away with doing this, okay? So what I'm going to do is I'm going to see how far I can get away with doing this. So I'm going to describe the late stages analytically, and what we'll find is that I'm going to feed material into the Hill sphere, which will be my outer boundary condition. Then I'm going to follow that material as it falls onto the disk. Along the way, I can calculate the velocity distributions or the velocity fields of the things coming in. I can calculate the density distribution of that infalling envelope. That gives me a source term that says what falls onto the circumplanetary disk. So I can calculate the structure of the circumplanetary disk. And with all those pieces in place, we can calculate the luminosity contributions for all the ways you generate energy. And with all those things in place, you can then calculate the spectral energy distributions to see what the radiation coming out of these things look like. And what's miraculous is that we have a formula, an equation for each and every one of those pieces. So this is the schematic. We have a planet, stuff comes into the Hill sphere, and the variables that I'm going to define are that at any given time, we have a mass of the planet, we have a mass infall rate into the Hill sphere. This is the net mass infall rate. Some stuff comes in the Hill sphere and immediately goes right back out. That's fine. I'm not putting that in. The m dot I'm talking about is the stuff that stays there, okay? It's Vegas, you know, what stays there, okay? And then we have to set the semi-major axis where the planet is rotating or where it's living. And finally, we set the magnetic field strength on the planetary surface. You might wonder, well, what does that have to do with anything? That sets the inner boundary condition of the disk. It only has a modest effect on what we're talking about, but it is important, so we're going to include it. Now, these four variables set the instantaneous properties of the planet. One thing that you might immediately ask is, how can I do that? Because the whole idea here is to do planet formation. Doesn't the mass change? Well, of course it does. But here's the deal. We can separate scales. The time it takes for stuff to fall from here to here, from the Hill sphere to the disk, is somewhat less than a year. The time it takes to make the whole planet is somewhat more than millions of years. So at any given time, if you want to know the instantaneous structure of the velocity fields, the envelope, and the disk, that adjusts on such a short time compared to the evolutionary time that you can fix the mass for purposes of doing that calculation and then vary the mass after the fact. If you have a solution for a given mass, you just secularly change the mass and have the solution for all of time. And that's the approach that we're going to take. One complication that you might care about or not is that there's actually 4 outer boundary conditions instead of 1. We've talked as if the Hill radius is the sphere of influence of the planet that matters, and for basically everything I'm going to talk about today, that is in fact the case. But there's also the Bondi radius. So when the Bondi radius is smaller than the Hill radius, you have to worry about it. In the late stages, you generally don't, but we'll put that on the board. There's also the disk scale height. The disk scale height is generally larger than the Hill radius, but if you make the planet big enough, it will pop out of the disk and you have to worry about the fact that there's a disk radius. There's also an astrodynamical sphere of influence that most people have forgotten about, which is almost the same as the Hill radius. So in principle, there's 4 outer boundaries. I'm only going to talk about the Hill radius today, but we can put in these complications should you want to, okay? So what I'm going to do next is I'm going to basically give you the answers, okay? So if you ask the question, if I feed material into the Hill radius at some rate m dot, and to start with, I'm going to feed it in isotropically, I'm going to choose the simplest possible orbits, so zero energy ballistic orbits. Oh, the sound speed. Yeah. Sorry about that. So if we feed in material at the Hill radius and then calculate orbits according to zero energy ballistic orbits, we can piece together the velocity fields and the density field, and you get solutions for them. Now, nobody likes to look at equations, so we'll simplify this for us. What you find is the same thing we find in star formation. If you take the non-spherical density distribution and spherically average it, then what you find is that on the outside, you get almost a power law with a density distribution that goes like r to the minus 3 halves. On the inside, where the inside means within the centrifugal barrier, you get a shallower density law that goes more like r to the minus 1 half. And the reason is that you're hollowing out the center of the configuration because not all the stuff can fall all the way in. And that has has 2 important effects. One is it funnels material onto the disk midplane, and that will be important for making the disk. And second, if you ask what's the optical depth from the planet out through the Hill sphere, which determines its spectral energy distribution, it will be far less in the presence of rotation than if it were spherical infall. Now, once we have the velocity field and the density field, I can calculate how much stuff falls onto the disk as a function of disk radius, and then I can solve the disk equation for the surface density. So here's your disk diffusion equation. If I just let stuff fall and sit where it falls in the disk midplane, I get the dash curve here. But if I make a steady state viscous evolutionary calculation, I get the series of colored lines where the different colors correspond to different values of viscosity. As I crank up the viscosity, more and more material flows in faster, and the disk mass goes down, and the surface density goes down accordingly. As we'll see shortly, this radius here is the planetary radius. The gold line is the magnetic truncation radius, which sets the effective inner boundary condition of the disk. Now, after all of this calculation, which gives you all of these crazy equations, you see that the lines are actually pretty simple. And to zeroth order, you always get a 1/r disk surface density. The details, the departure from the 1/r is what you need for the disk to satisfy conservation of energy and conservation of angular momentum as the stuff falls on it and it adjusts to being in a disk. And depending on what you use as a source term and what your assumptions are, you'll get a slightly different departure from 1/r. But what's remarkable is that over all the parameter space that we care about, the solutions are damn close to 1/r for almost all the case, right? So you can kind of take that result to the bank. It's not completely obvious beforehand, but after enough time, it becomes obvious. So again, let me put this in context. I've said that we're using these four masses. I can do this calculation as a function of planet mass, semi-major axis, the net infall rate into the Hill sphere, and I use the magnetic field strength to set the inner boundary. The calculations I'm showing you today are the first go around on this, and we've made a certain set of assumptions to make our life easy. We have since then generalized this because we can use different angular momenta. We're assuming in this calculation that the rotation rate at the Hill sphere is the mean motion of the orbit. But when flow comes from the disk into the Hill sphere, you can have a deficit of angular momentum. There can be an angular momentum bias. We can put that into the calculation. We've assumed here that we have zero energy ballistic orbits, which are just mathematically the simplest ones to use. But we can also do the orbit calculation for different additional conditions at the Hill radius, different starting radial velocities, and so on. So we can choose our energy at the Hill radius to be different, and we can do that calculation too. We can also, instead of assuming isotropic infall, we can use an angular dependent infall. Some of the numerical simulations show that the material coming into the Hill sphere does have angular dependence. The bad news is that some say it comes in along the poles and others say it comes in along the equator. So you're not sure which one to use. So we use them all. We can have a angular function that's more polar, isotropic, more equatorial, and we can do the calculation for all of those. And we can also change the outer boundary condition of the disk, which I won't have time to say much about. So the point is that all of what I'm showing you here can be generalized. And I see we were already losing one audience member. So
I agree with all of
excellent. So this is actually the slide that Konstantin made me make. He said, Fred, what if we have not one, but two magnetic radii? And here's what you got. So those of you who do star formation are well aware of the fact that if you have accretion through a disk, it will butt up against the magnetic field lines of the central object, in this case, the planet. And once the ram pressure of the flow of the incoming flow is as big as the magnetic pressure pushing out, you get a truncation of the disk. And there's a truncation radius, which was derived, I think maybe Roger Blanford was one of the first to do this here at Caltech many decades ago. You get various versions of the equation that looks like this. Now, we realize there's a second radius that matters. If you have magnetic field lines like this, and you have material flowing onto it, there will be a point here, which corresponds to the point where the ram pressure of the material falling from the top balances the magnetic pressure from this field line pushing up at the horizontal point, where the horizontal point is defined to be the point where this is flat, so that material falling to the left of the horizontal point will come onto the star, and material falling to the right of the horizontal point will fall back onto the disk. So this field line, this set by this point here, defines an effective magnetic capture radius. So what it does is it increases the cross-section by which the central planet, in this case, can actually capture in falling material, and it has a nifty little analytic form that you can calculate. And it's a little bit larger than the truncation radius, but only by a little. And that's what you get. So far, what we have done is we have tried to describe the flow from the Hill radius onto the planet. Well, first onto the circumplanetary disk, and then onto the planet. And we have succeeded in calculating the velocity fields, the density field, the surface density, the inner truncation radii, and we have this analytic picture of this whole structure. And Shri has a question.
Yeah. So magnetically, you're assuming that the level of ionization is sufficient. I thought this all happens with gas.
For it to matter, you absolutely do have to have the ionization large enough to couple. So for most of the parameter space that's relevant, you don't need a fully ionized gas by any means. In the interstellar medium, in cold cores, which are only 10 Kelvin, if you have an ionization fraction of 1 part in a million, that's enough to couple. Here, you're much more coupled, because instead of having a temperature of 10 Kelvin, you have a temperature of 1,000 Kelvin. And there'll be, you're also at sufficiently higher densities. So both the radiative and collisional ionization will be larger. I actually don't know what the number is off the top of my head, but it will be bigger in the interstellar than in the interstellar medium. And in the interstellar medium, you are coupled. So good question, important to see, but I think we're coupled enough. Also, as we'll see, this just sets exactly where you put the inner boundary condition, and that will be sort of the least important thing that will affect how these things look. But good point nonetheless. And we can come back to this later, but let me continue. Any other important questions? Yes?
I don't understand the second magnetic radius, because it's here hitting that.
Because what?
The material at the screen where the box is, the second magnetic radius, it is dominated by the gas ram pressure. Why is it sliding along the magnetic?
Oh, well, it can't, the idea is that if this field line sets the pressure beyond which you can penetrate, it can't go any further down because the pressure is bigger, right? So it will either go to the left or right. That's this one. Well, oh, the difference is that the first magnetic truncation radius is set by the balance of ram pressure of the flow from the disk inward. The second one is set by the ram pressure of the infall from the envelope. So you're balancing ram pressure in both places in a similar way, but you're balancing two different sources of ram pressure in the two different cases. Okay. So, having said all that, the next question is, well, what do these things look like? We have to do some kind of radiative transfer treatment to see what the spectral energy distributions of these forming planets were to look like, okay? So, the first thing you have to do is set what the luminosity contributions are. And there's a lot of them, and you don't want to see the equations, so let me go to the words. What you have is that the infalling flow has a direct component that falls onto the surface of the planet, dissipates energy, and that gives you a direct accretion luminosity. You also have a direct accretion luminosity onto the disk because material comes from the envelope, smashes into the disk, dissipates its vertical component. You have a luminosity contribution. In addition, the material that's about to hit the disk doesn't know in advance that it's going to become part of the disk. So it doesn't have the right angular momentum to be part of the disk. It will immediately mix with the pre-existing material and obtain the right rotation curve. And in doing so, it has to dissipate energy, thereby giving you another luminosity contribution, which is what I call a mixing luminosity. And then, of course, the big thing is that most of the material will fall onto the disk, not onto the planet, but it eventually has to get onto the planet, and the viscosity will move it inward, right? So most of the energy is generated by viscous dissipation in the disk, and it sets up a viscous accretion flow. You can, of course, include the intrinsic contraction luminosity of the planet, but that happens on a somewhat larger scale, so it's a pretty small contribution. So let me just move on. What I want to do next is I'm going to do the simplest possible treatment of the radiative transfer. So this is what I call my spherical cow approximation. So we take this envelope and we'll spherically average it. So we're taking a non-spherical density distribution and spherically averaging it, which does not give you a spherical solution because you've included the fact that you had rotation, which keeps material from falling all the way in. So when you spherically average it after the fact, you have retained that cavity in the middle or that lack of material in the middle. So I'm going to make that assumption. Bear with me. And then I'm going to make the optically thin assumption. The radiation from the central planet and disk can be somewhat hard, as in K-band, like 1 micron-ish. And that can be absorbed by the envelope. But the material that is re-emitted by the envelope is emitted at longer wavelengths where the opacity is lower and those photons get out. So the emission of the envelope is in fact optically thin. And if the emission is optically thin, you can write down the luminosity and the spectral energy distribution analytically. And you get this spectral energy distribution. Now, you'll immediately have an objection, and you should, because you'll say, well, the real density distribution is not spherical. It looks like this, for example. How do I get away with this? So to try to convince you I'm not 100% crazy, what we did was we did 3 treatments. We have the equivalent spherical envelope analytic treatment, which I just showed you. And that's the green curve here, the solid green curve. The 3 dashed components are the planet, disk, and envelope contributions for this particular case. This particular case corresponds to a mass of 1 Jupiter at 5 AU with a mass m dot of 1 Jupiter per million years, but you can do this for any of them. But then in addition, we made an honest, or at least mostly honest, ray tracing radiative transfer code in full 2D. And that gives us the red curve. And then we use RAD 3D-MC, which is a Monte Carlo radiative transfer code, completely different code, which gives us the purple curve, which gives us the same thing. The difference between the purple curve and the green curve here is actually not due to a difference in the physical assumption. It's due to the fact that RAD 3D-MC makes it really difficult to put in the same disk properties at large radii as the other 2 codes. So that's more a statement of our laziness than a difference between the codes. So I would like to argue that the 3 codes actually give you the same result. And given that the 3 codes give you the same result, for purposes of the next minute anyway, I'm going to use the simple one. And I'm going to answer the question, what do these things look like? And moreover, how do the spectral energy distributions, namely what these forming planets look like, how does that vary with the input parameters? Because that's what you really want to know, right? If I make the mass bigger, what happens to the spectral energy distribution, and so on. So here we go. So here's the spectral energy distributions as a function of mass. I'm going to fix m dot at 1 Jupiter per million years. The distance of, or the semi-major axis will be at 5 AU. and the boundary condition is set by a 500 Gauss magnetic field. Then I'm going to vary the mass from 0.1 to 10. And not surprisingly, as you go from low mass to high mass, you get.
500 Gauss is the dipole field of the protoplanet.
Yes. Yes. It's a dipole field on the surface of the protoplanet. It falls off rapidly, right? Because 1 over r cubed and 1 over r to the 6th for the pressure. This might be a little high. It doesn't actually affect things too much. I will show you how it affects in 3 slides. But the point here is that for this boundary condition, you vary the mass and you get this sequence of spectral energy distributions, and they get brighter as you get bigger in mass, and they get bluer. If, on the other hand, you fix the mass and you change the mass accretion rate from 1/10 to 10 Jupiters per million years, then, not surprisingly, when you go to higher mass infall rates, you get more luminosity, you get brighter. But here you get redder, and that's actually easier to understand because the increase in m dot, the mass infall rate, increases the optical depth, which means you absorb more of the central source, more is re-radiated at long wavelengths by the envelope, and there you go. What's sort of interesting is if I change the magnetic field strength, what you find is that as you make the field stronger, you increase that cavity, so you get a little bit brighter and a little bit bluer. The reason why you get brighter is that you're increasing the truncation radius, so you have more material that's falling directly onto the surface of the planet from far away, giving you a little bit more bang for your buck. And you have a little bit less optical depth, so you're a little bit bluer in color. And finally, and this is one of the reasons why you want to actually have a model like this in the first place, is you can ask, well, what happens if I move my planet inward? So I'm going to move the location from 10 AU to 1/10 of an AU. And what you find is that as you make the planet go further in semi-major axis, you shrink the Hill sphere and you shrink the sort of ranges of temperatures and densities that you sample in the disk and the envelope, and you make the spectral energy distribution narrower and narrower. So as you make the planet further out, you get a wider non-thermal, non-black body like spectral energy distribution, and as you move it in, it becomes narrower and narrower. Now, the reason to do this is that we are just now on the cusp of being able to measure planets in the process of forming. Right now, depending on how you count, there's 1 to 6 data points where you can basically measure what might be a forming planet at 1 wavelength. So this is early days, and I don't have time to go into all the ins and outs of the observations, only to tell you that they're all coming. So in the next decade or so, what we hope is that there will be observations of planets embedded in disks in the process of forming, and then going through the exercise that we just went through to look for the spectral energy distributions will be a useful enterprise. Okay. So before I run out of time, let me cap this off and switch over to the other topic. What I've presented to you is I've given you an analytic description for how a planet looks during this 3rd stage. And how it looks depends on its velocity fields and density fields that we can calculate. It depends on the surface density of the disk that forms, and we can do that. We've talked about the magnetic truncation of the inner edge, and a new capture radius, our new magnetically informed capture radius. And then we use all this to determine the luminosity and finally the spectral energy distributions. Now, let me say once again, what we've done and the approach we've taken is we've got a model, a picture, and hence a spectral energy distribution for each mass, each m dot, each location, and each boundary condition set by the magnetic field. If you want to put an evolutionary sequence on this, as time goes on, all of these things will be a function of time. If you know how m dot and position depend on time and mass depends on time, you can piece together how these things look over time. So you can use this framework to do that, but I have not shown you that. Now, there's one interesting thing that I like to emphasize here, and that is we want to compare what we're doing here in the planet formation problem to the star formation problem. As some of you have worked on star formation. The disk has a much easier time of doing its job in the planet realm than in the star formation realm. And here's why. In the star formation problem, the disk is 100 AU, as we saw. That's 10 to the 4 times bigger than the star. So in order for material that falls onto the disk to make its way onto the star and form a star, it has to change its location by a factor of 10 to the 4 at radial scale. Okay? And we also know that the star formation timescale is only about 1/10 of a million years. So you have to move a factor of 10 to the 4 on a time scale of 1/10 of a million years. Now, compare that to the planet formation problem. Here, the dynamic range of this disk and planet is only a factor of 100 or maybe 200. So you win by a factor of 100. And the time it takes is 3 to 10 million years. So you win by almost another factor of 100. So it's actually 10,000 times easier for the circumplanetary disk to move its material through viscous action than it is for a circumstellar disk. Now, those of you who remember the star formation problem, remember the early stages, viscosity can't keep up with the infall, and that's why we study gravitational instabilities. We study gravitational instabilities because we have to. The thing becomes gravitationally unstable. And that is what moves the material, at least in part, from the disk onto the star. In this case, material falls onto the circumplanetary disk, but it's 10,000 times easier in this glib way I'm describing it. It's that much easier to move material from the circumplanetary disk onto the planet, and viscosity can easily keep up as long as alpha is bigger than 10 to the minus 4 or 5 or something like that. So unless you set alpha equal to 0, viscosity can carry the day. Okay, now, everything I told you can be generalized. We can put migration into it. We can put competitive accretion into it. One thing I want to say is that, and I didn't have time to show you this, we've done quite a bit of additional work where instead of having an isotropic flow into the Hill sphere, we have an angular dependent flow. We've also did quite a bit more analytic work where instead of just assuming that we're in solid body rotation at the mean motion, you could have an angular momentum bias. We can do all of those things and do all of the solutions, and we have, but I'm not going to overload you with them, only to tell you that we have them. So this framework can be generalized in many, many directions, even though I've only showed you sort of the spherical cow, easiest version of this. The million-dollar question that I haven't addressed is this one. When the planet is gaining mass, we're in this picture just feeding material from the circumstellar disk into the Hill radius or into the Hill sphere and then onto the forming planet disk system. What stops it? So I want to spend the last few minutes of the talk trying to answer that question. So the basic idea is this. I'll tell you a story. Michael Meyer came to me and he said, well, Fred, of course planets form their mass because the disks go away, which is not wrong. The disks do go away. And if they go away, then that will bring an end to the accretion. But the problem is, as I'm about to show you, to 0th order, the distribution of disk lifetimes is exponential, but the distribution of planet masses is power law. So if it's only a matter of the disk running out of time, why isn't the mass distribution an exponential? Why is it a power law? Or how do you mathematically turn an exponential into a power law? So I said, Michael, I'll prove to you you can't do this. And unfortunately, I found a solution. So it's not a very good one, as you're about to see. But let's see how this goes. So first of all, here's the data on the disk lifetimes. I can hear Lynn's mind exploding. You can't really know the ages that well. This is like too simple. And she's, of course, right. But nonetheless, we're going to go with it. So this is the fraction of disks we see in clusters is a function of age. It has this form. It's given to us by Jesus Hernandez. And if Jesus tells me something, I listen. So this is the right data. And if you want to look at it in exponential form, we can plot it in a log-log plot or semi-log plot. And you can try to tease out the half-life. It's not a great exponential, but if you want to fit an exponential to it, you would do so with a half-life of about 3 million years and an e-folding time of about 5 million years. And for the sake of simplicity, that's what I'm going to use for the next 5 minutes. Now, as far as our target is the observed mass function, even after all this time, the mass function of giant planets is not 100% well known. I think that's fair to say. And if you go back to this Cummings 2008 paper, he has a histogram. They have a histogram of the mass function. This is in logarithmically spaced bins. So if it's flat on this, it's a 1 over m mass distribution. And you see it's pretty flat with a little bit of deficit at the high mass bin. And you can fit a power law to it with a slope of 1.1 to 1.5, with 1.3 being the sweet spot. If you then dial forward to 2021, you get another histogram plotted logarithmically, so flat over m. You see flat, 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 a little bit of deficit in the high mass end. If you fit a power law to it, you get a slope between 1.1 and 1.5. This is all getting pretty familiar. So to 0th order, the observational landscape is that we see an exponential distribution of disk lifetimes and a power law distribution of planet masses with a slope of about 1.3. Now, there's lots of uncertainty in everything I just said. You can also look at the total mass function with gravitational lensing and whatnot, and the giant planet part looks very 1 over m-like as well. So what I want to do, and I'm going to run out of time, so I'm going to skip forward just a little bit. We need some complication. If you just say that your theory is the mass of a star is equal to m dot times time, and m dot's just a number, then the distribution of time will be the distribution of masses. 5 minutes? Okay. I better hurry. But that's not what we see. So that's why you have to turn an exponential into a power law. Now, of course, the mass accretion rate, m dot, is not necessarily a function or a constant, but you need some distribution of that. So here's what we're going to do. We're going to say that the final mass of the planet is the mass at the end of phase 2. Remember, I wasted many minutes at the beginning of the talk explaining what it means to be going from phase 1 to phase 2 to phase 3, which you might not remember, but that's why I did that. At phase 2, the end of phase 2, the beginning of phase 3, we start to accrete mass rapidly. So the final mass will be the mass you have at that stage, plus the integral of m dot over time from that time to the end. This is exact by definition. We don't really know anything to put in it, but it's the exact thing. But here's the thing, and this makes our life simpler mathematically. I'm going to change variables. So I'm going to measure a new time, which is the time since the end of phase 2, or the end of phase 2, the beginning of phase 3. And t wiggle will be the time left after you've reached phase 2 and begun phase 3. Now, here's the beauty of the exponential. T wiggle also has an exponential distribution, right? Just like radioactivity. Doesn't matter how many nuclei have decayed, the ones that are left will still obey an exponential decay law. So these disks, doesn't matter how many you have gone by the time you've reached phase 3, the ones that are left will still have an exponential distribution. So we know the distribution of t wiggle, and it's exponential. I'm going to assume that the mass accretion rate into the Hill sphere goes like some power of the Hill sphere. I can do it for any power p. Since I only have 3 minutes left, I will use 4 for what I show you. That's because that's what the numerical simulations show we should use. And then I'm going to put in a random variable. I could put in 1 or 2 or 3. I'm only going to show you the results for 1. And I'll show you how that comes about in the following way. The mass accretion rate onto my planet will be some random number, which I draw from the distribution, times some constant, which just sets the scale, times the Hill radius to the fourth power, which is the mass to some power. And that lets me take or include the physics that a larger planet will eat mass faster. Then if I do one slide's worth of math, I can calculate the planet mass as a function of t wiggle. I can invert that to define a time scale. And then I have to do a couple pages of math to convolve the distributions of time and this random variable together. And what you get is a form like this, which is a power law times an exponential integral. And there's one variable that matters. Remember, we had this one constant that we haven't specified in the m dot. Tau is the half-life of the exponential distribution of disks, which is 3 billion years. So that's a known quantity. And this is just a scale factor, the mass at the end of phase 2 times the mass of Jupiter, just to, because that makes my formula simpler, but I could use it in different form. So setting m naught is essentially the same as setting this constant, which sets the overall scale, the overall time over which planets form, modulo the mass dependence. So I could then look at my mass function I get out of this as a function of that one parameter and compare it to the power law that I think that we see. And if you make that mass large enough, you get the blue curve, which is close enough to the black curve, which is what we think we see, that it's good enough. Okay. So I think I'm out of time. So let me just wrap up. You can use this method and you can build it in many, many more complicated ways to build theories of the mass function. The minimum complication you need to turn an exponential into a power law is you start with the exponential lifetime distribution, you let m dot increase with the planetary mass, and you put in some random factor. And when you do that, you get something that's close, at least kind of sort of close, to the observed distribution of masses. And if you believe all of this, and this is where we're going off into speculation land even further, you can do this as a function of stellar mass. And if you do this as a function of stellar mass, what you find is that for really low mass stars, you get a steeper mass function because you run out of mass. And at really high mass stars, you get a steeper mass function because you run out of time. So the sweet spot for making the most stars through core accretion is actually something sort of close to the solar type stars. So let me just put my conclusions up here. I see that I'm being yanked off the stage. Thank you for your patience, and I will take questions. So.
$87.99.
Oh, yes.
Those brown dwarfs. Based on that's what fragmentation should be.
Yeah.
Brown dwarfs here. To what extent does that depend on the mass of the star? Since in this case, it looks as though some of those objects, some of those planets may be more planety than brown dwarfy.
Yeah, no, that's possible. It's quite possible that those particular planets, they could either be the low mass end of the gravitational instability planets of brown dwarfs forming at 100 AU, or they could be the high mass end of planets forming through core accretion, which have a sweet spot more at 10 AU, and they got moved out. I saw the data from one of your colleagues today that they're high in metallicity, which is suggesting more the latter than the former, but that very well could be for that system. I think, well, I would like to think that my general statement that gravitational instability produces brown dwarfs at 100 AU is relatively robust, and that most of the planets form through core accretion. If you're saying 3 more than I thought formed through core accretion, then my statement that I'm going to do core accretion is still good, right? But that's a very good point. Did I answer your question? Yeah. Okay. Oh, David.
Showed early on the standard core accretion model that comes quantitatively from Pollock and Bodenheim.
Yeah, yeah, it was originally Pollock and
And
Bodenheimer.
it shows short time scale, the growth of heavy element component. And then over millions of years, a very slow process.
Yeah,
And that mass, which is often quoted with 10 Earth masses, comes of course from the surface density of the disk and the assumption of a disk doing nothing except it sits there.
yes, yes, yeah, yeah. Yeah, no, it's too simple to be real. That,
What your point of view is about whether that is reasonable. And you mentioned migration. I mean, over millions of years, you would expect the disk to evolve, surface density to evolve. And so this simple picture of very gentle growth with hill speed before you get runaway might be wrong. And what I'm getting at finally is it seems to me that the problem is inextricably connected to the formation of the star and the disk around the star. And so it's not sort of universal anymore. Now, maybe a lot of what you talked about later in your talk is independent of that, but surely you can't talk about the formation of a giant planet without talking about the formation of the star. Maybe you're doing that anyway, but I'm just trying to clarify the way you think about the problem.
well, you just asked 3 hours worth of questions, but I'll do my best. So I fundamentally agree that the planets form in disks which form around the stars. So you're absolutely correct that fundamentally the star formation problem informs the planet formation problem. I also agree with you that the way in which you go through phase 1 and phase 2 is certainly more complicated than my simple description. Once you get to phase 3,
In some sense, it may not matter, except you have to.
well, it matters for some things and it doesn't matter for others. That you ask me what I think. So for purposes of asking the question, what does the planet look like during phase 3? So if I look at it with a telescope, can I identify it as such? Then I just need to know local properties and I can do the calculation that I did. And that was my goal. But another question that other folks might want is, well, how often does this work? How often do you even get through phase 2 to get to a planet? What is the occurrence rate of giant planets as a function of semi-major axis? And how do I explain that? That I need to know all the things that you just said. I need to know the star formation thing. I need to know about migration. And I need to know the details of how the disk treats the object when it's going through those different phases. Yeah, I did have competition on a slide that I passed through quickly. The one thing I will say though, which I'm hopefully will simplify all of our lives a little bit, is that if you go back to the occurrence rate as a function of semi-major axis, they're now nicely peaking at the ice line. And if that is really robust, that tells us, because I think that the ice line is in fact the sweet spot to make a planet, because the further out you go, the clock runs slower, the harder it is to do. But if you're inside the ice line, all the rocks don't have ices on them. There's 3 times less mass than solids and they don't stick together. So right at the ice line is the best place to make planets. And that's right where we see them, apparently. If that's the case and they stay there, then they don't move that much. If all of them move from the ice line into a hot Jupiter, then migration would be a huge part of the problem. And everything I said would require lots of revision. But if everything stays kind of close to the ice line, and apparently many of them do, then I don't have to, I certainly have to worry about it eventually, but it's not as big of a problem. So I'm hoping that the ice line distribution saves us. But that might be optimistic on my part.
So back to the ionization, what is the typical density at which this impulse particles for semi-major?
I don't know the number off the top of my head. The surface density is going to, of the circumstellar disk is going to be measured in 100 to 1,000 grams per cubic. And then the scale height is going to be a half AU. So if you put those numbers together, you get 10 to the
so that's
10-ish.
So the ionization Could be a problem because the one you talked of, the giant polar bear clouds, the densities are much smaller. And in ionization, there would be from cosmic rays to be no controversy, but let's say that's the case. Actually leads to very small ionization pattern, just with directed.
Oh, so you're saying we'll be shielded from cosmic ray ionization?
I'm just telling you that you can GMCs.
Uh,
And I just told you that ionization there is from cosmic rays.
oh, okay.
That is fixed. So if I increase the density of this gas, which is much more dense than GMCs, then ionization rate goes down by precipitously. But I was thinking maybe there's a star that's formed and that is rotating rapidly. And so maybe, I don't know enough of that, which state it is, but it could be, there could be a supply of X-rays actually from the central star. And that is the one actually sets the ionization rather than the GMC idea. Which is
Oh, I see. Yeah, that's.
So it's actually what.
Oh no, that's a very good idea. I should be more careful about the ionization in general.